Do you have a class before this or no?
Yeah.
Okay, so you understand my struggle of. I mean, fortunately for me, my class is right next door, but it's still that thing where like people are asking me questions after class. So I'm like, and then I come in here with like 2 minutes, but it's like at least it's literally next door. So if I'm ever late, you can just go next door and be like, Travis, where are you? And I'll be like, oh, sorry. That probably won't happen, but anyway, so a couple of quick announcements. I posted some stuff to Blackboard. So I have posted, it's called like group submission or something like that. I don't remember specifically what I called it, but it's submit who you want to work with on your assignment. At this point, you probably worked in groups for Python, right? So unless you had a falling out, you're probably working with the same people. So you can submit it. You don't have to work with anyone. You can work by yourself, but up to 4 people. I made it for grades. It's out of 1. It's not actually going to affect your grade if you don't do it, though. So don't worry about that. That's just, so if I put it for out of 1, then Blackboard is just going to be like, hey, you have a thing due. So it's just for me to organize you into groups so it's easier to like grade stuff, right? If you're all in a group in Blackboard, then I only have to grade it once, right? For all 3 or 4 of you or however many are in a group. So you can just go in there and say, I'm working by myself, or, myself and these other 2 people are working together, and then I will deal with it. I think I made it do it like the end of the month or something. But again, if you don't submit it, if you forget or just don't get around to it, then all that's going to happen is I'll probably be building the groups, and then I'll see you didn't fill it out and you're not in any groups, and I'll just email you and be like, are you in a group? Did you just forget, or are you by yourself? And then I'll just figure it out from there. So no big deal, but just that's what that's for. So if you don't submit it and it's nagging at you, I will hide it eventually. So then it will stop nagging at you. I also posted the submission for quiz 2, I guess, technically, on Blackboard. That's the one we're going to do today. Something I forgot to mention for quiz 1, but for future quizzes, is you have the option to hand it in to me physically in class or online. So the problem with handing it in physically is it's not a problem, but Blackboard doesn't know that you handed it in to me. So what it will do is if you don't do something, like submit just, I handed it into you in class, once the due date passes, Blackboard is going to say, you missed something. Right? And I can't hide that because then it hides the grades from everyone, and that's bad. So my advice, if you hand it in physically, if you just don't like seeing the notification that says, hey, you missed an assignment, then you can just go to the like quiz 2 submission and just say, I handed it in to you. And then click submit, and it won't matter at all. It just won't nag you that you missed an assignment anymore. So that's just a consequence of me doing sort of a mixed thing where you can either hand it in person or hand it in online. If you hand it in online, it doesn't matter. It's just I'll grade it there, and then it won't complain to you. But if you hand it in physically, Blackboard will complain and say like you missed an assignment. So just wanted to mention that so that nobody panics on like the Sunday after it's due and they're like, why is it saying I didn't hand it in? I handed it in to you. Well, it's because it's sitting on my desk and I'm still grading it, and I probably won't finish until Monday. Okay, I think that's all I have for that. So we're just gonna jump straight in. So last class we did a sort of rudimentary introduction to logic and logical operators. Most of them are ones that you'd be familiar with already. So we had the idea of negation, which just flips essentially the truth value. If it's false, it becomes true. If it's true, it becomes false. We have the logical AND operator, which is if they're both inputs are true, then it returns true. We have the logical OR operator, inclusive, I should say. So if at least one of them is true, we return true. The conditional, this was sort of the weird one. This was the one I kept calling like a promise. It's hard to understand initially. The important part is just think of it like I'm trying to prove something is true. So I start with a hypothesis, right? Like some math theorem or just some other result. I start with a hypothesis that I can see is demonstrably true. Then I try to prove that something follows from it. If P, then Q. Either Q is true or Q is false, right? I started with something, and I'm trying to prove something else, either what I'm trying to prove is true or false, right? If it's true, great, then the whole statement is true. If what I tried to prove ended up being false, then the whole statement is false. I also explained it's like a promise, all kinds of things like that. When you see the truth table, that's the only thing that's going to matter, right? Is just the truth table. We also have this biconditional, which basically behaves like equality for logic, because if the left-hand side is true, the input here is true, and this is true, then the whole thing is true. If this is false and this is false, then the whole thing is true. It's checking to see if the inputs are the same on both sides, right? If they're different, that's when we say it's false. So when they're the same, we say it's true. So those are the operators we have. I briefly mentioned exclusive OR, but I'm not going to put too much emphasis on that. If you're looking at logic gates, you might need to know it more, but that's not what we're going into too much. So with that said, there is sort of a nicer way to organize information, right? So especially this one is kind of hard to keep track of when it's true and when it's false. So it'd be nice if we had sort of like a compact way of keeping track of everything, right? And that's where a truth table comes in. So we can more compactly organize information about operators with a truth table. So I kind of just in passing gave an example of one last class, but we're gonna do more complex examples and the truth tables for all of these. So the way we build it essentially is we start with our input here, right? And then we say, okay, we have essentially more statements or our outputs there. So what happens when P is true and what happens when P is false? Well, stuff, right? Whatever this is going to tell us what happens when P is true and when it's false. So as an example here, let's use the simplest operator we have, negation, right? We know logically how that works, right? It takes whatever P is and flips it, right? True becomes false and false becomes true. So we can say, okay, this is essentially our input, and this right here is our quote-unquote output. So we plug in true, not P gives us a false, and when we plug in false, not P gives us a true, right? So this is like the simplest truth table we could possibly build, is this operator here. So what if we want something more complicated, right? Well, it's not more complicated per se, it's just more inputs, right? Right here, we're restricted to one input. Well, what if we have two inputs, right? Like the AND operator, it's got P and Q. Well, we can still collect it in the same way, right? We can build a table for it. So let's build a truth table. For P and Q. So if we think about it, we've got our two inputs here. And for these inputs, they can both be true or false, right? P can be true or false, and Q can be true or false, independent of each other. So that means P can be true or false, right? But then, if we just said, well, Q could be true or false, you can see we're missing stuff here, right? We have true, and we have false and false, but we need false and true and false. So I have sort of like a more pattern-oriented way to do this. This captures the situation where Q is true, essentially. But now we just need when Q is false, and we just essentially write down the same thing, but Q is false. And we look and we say, okay, we got true, true, false, true, true, false, false, false. We've got everything, right? There's 4 possibilities here. Okay, so from this, our output is P and Q. So this time we have 2 inputs, input 1 and input 2. And so the reason why I'm kind of phrasing it that way is when we have more complex statements here than just P and Q, thinking of it in terms of this is input 1 and this is input 2, and I AND them just makes it easier to build truth tables. So in this case, P and Q, or input 1 and input 2, that's true when they're both true. Otherwise, it's false, right? So we take a look at this. True and true, that means we write down true. False and true, well, we write down false. Yeah. True and false, we write down false. False and false, we write down false. Now, I kind of mentioned it before, but true and false have an obvious correlation with binary, 1 and 0. When it comes to truth tables, you can use either or. So whichever one makes more sense in your head, pick one. I'm a mathematician, so I've gotten so used to doing this. Even though I also am a programmer, it's like I'm so used to writing T and F. Although another student in the previous section pointed this out, like 1 and 0 are so much more visually distinct than T and F, and I was like, oh yeah, that's true, isn't it? So if you're comfortable with 1s and 0s, it probably looks cleaner because like my T's and F's, sometimes if I write them quick, they look kind of the same. Or it's hard to mix up 1 and 0. But the point is you can use either, right? So if you want to use 1s and 0s, go for it. If you want to use T's and F's, go for it. I'll accept either. There's no sort of set standard for me. You just whichever you're comfortable with. I guess technically if you wanted to use different letters too, that would be fine. But I mean, you'd have to write down this means true and this means false. Okay, from this, we can kind of get the rest of the truth tables, right? Because all the other operators we had were 2 inputs, right? A P and a Q. So, well, we can just extend this table, right? Because we have some other operators. We have P or Q. And then we have P implies Q. And then we have P if and only if or biconditional Q. So we do the exact same thing here, right? Except now this doesn't matter for each single one of these, right? We only care about what's P, what's Q. Input 1, input 2. So P or Q is true unless both the inputs are false, right? So that means here is true, here is true, here is true. The inputs here are both false, so we write false. This is the weird one, but I mentioned, think of it like a promise. The only time where I actually really break a promise to you is if you kept your side of the bargain and I didn't. So in this case, we write down a false. Every other situation, we write down true. There's only one situation where this statement is false. So when you're dealing with truth tables involving this, it's just keep that in mind, right? When input 1 is true and input 1 or input 2 is false. Then we write down false. Otherwise, you just write down T's, right? So you can just look, you could say, okay, well, input 1 was F. All right, doesn't matter. I just write down T. The only time you care is T implies F. Then you write down an F, otherwise you fill it in with true. This one here is sort of like equality. It's just checking, are they the same? Right? So if they're both true, we write down a true. If they're both false, we write down a true. And otherwise we write down false. And so now we've sort of captured all of this in like a very compact way, right? We don't really have to, if this is in front of us, we don't have to understand anything really anymore, right? We've just got this sort of broken down zeros and ones, right? Yep.
How did you solve the last one?
This one? So this here is true when both inputs are the same. So when P and Q are the same thing. So here, true and true, here, false and false. So they're the same. Otherwise, it's false.
What about implies one, the third one, P implies Q?
So this is, so I last class I gave like a couple different ways for why this is what it is. But this is just false only when input 1 is true and input 2 is false. Otherwise, it's true. This is I had like an example with numbers that I use, and then I did the promise one. Another way to think about it is this is a hypothesis and then a conclusion. So if you start with a known true hypothesis and arrive at a false conclusion, then that means the whole thing, what you just did was false, right? But if you start with a true hypothesis and get a true conclusion, you just proved something, right? From A followed B. Okay, so one thing I want to note here is that these are sort of stealth troubleshooting in a way, in that we can notice that with one input we had 2 rows, right? True or false. In this we have 2 inputs and we have 4 rows. So what if I had 3 inputs? How many would I have? It is kind of a trick question, but so I have 3 inputs, P, Q, and R. How many rows do I expect to have?
8.
Yeah, because it's just powers of 2, right? It's counting argument. So in each one of these situations, I have 2 choices. So let's say instead I was building this table. And then stuff. It doesn't matter what's after that. So we ask, how many choices do I have for P? I have 2 of them. How many choices do I have for Q? I have 2 of them. And how many choices do I have for R? I have 2 of them. So right here, we already know this is 4 of them, right? For every choice here I make of that 4, I can make another 2. Right? So from every single one of these, I get another 2 choices, which means there's 8 total, right? So this is also just a combinatorics thing. In this case, when you're counting like this, you multiply the number of possibilities. So if this were 3 instead, then the same would still hold true, right? It would be 2 times 2 times 3. We'll talk about counting and combinatorics later. But the point is, this is 2 to the 3, or 8 rows. So for n inputs, your truth table has 2 to the n rows. And that's how, I mean, they're sort of self-troubleshooting, right? If you look at your truth table and you were working on it, you're like, okay, I have 4 inputs, P, Q, R, S. I only have 15 rows written down. You'd be like, I missed one. Great. If you have 16 rows, doesn't mean they're the right 16 rows. It just means, well, at least that's correct, right? So that this is just helpful, right? Just knowing how many you should have just lets you know that you haven't missed anything. So let's build a more complex one, right? Because all we've done here is we've just taken truth tables for our basic operators, right? But what about compound statements, right? Can we build truth tables for that? Sure. Why not? So we can build the truth table for, what do I have here? P and Q, or not R. So I hope I have enough room to write this down. One thing you'll see pretty quick with truth tables is even with 3 inputs, they take up a lot of space. So it just, sometimes we run out of space. So I'll do my best. So we see here, we have 3 inputs, P, Q, and R. So let's just start with that and see how we want to proceed here. So the way I like to do this is sort of a pattern-based approach. So we just write down trues and falses, alternating, until, hey, wait a minute. We have 3 inputs, 8 rows, we stop. right? Now we've written down 8 things, so we're going to have 8 rows. Now we look here and we sort of motivate ourselves from this. I wrote down 1T, 1F, 1T, 1F. Then I wrote down 2 T's, 2 F's. I'll do the same thing here, right? I'm going to double it. Like that. And I say, hey, wait a minute, I just doubled the amount. Let's do that again. Right now, let's write down 4 T's and 4 F's. And now we just check. So I just described, okay, let's just try this and see if it works. So we should have captured everything. We have 8 rows, but do we have any duplicates? Because if we have duplicates, then that means we missed something. But if we don't, then we've got everything, right? So let's see, we've got true, true, true. FTT, okay, that's different. TFT, that's different. FFT, that's not up here. TTF, that's not up here. FTF, we're good. TFF, we're good. FFF. So we got everything different from each other, which means we have 8 rows that are all different, which means we've captured everything. So this pattern kind of removes a lot of the work of like, do I have everything? Right? If you just do that. Some students, I have seen it, they just write stuff down. And that's totally fine, right? If that's how your brain works, you're like, I don't like the pattern. I just want to write stuff down to see if I got everything. Go ahead. Just remember you should have 8 rows. I recommend doing a pattern because I'm lazy. And why work harder when we don't need to? Okay, so those are our inputs. That's all of our possible inputs for. You can think of this compound statement as a function, right? Or a conditional, or it's a conditional if statement, right? Like what are the pieces in there? So in this case, we have P and Q or not R. So we sort of got 2 different statements here, right? We've got P and Q, and we've got a not R. And from that, we build a bigger statement, right? We build P and Q or not R. So we can just write these down individually, P and Q, not R. Right? And then once we have that, then we form the full compound statement. So that would be P and Q or not R. And we see this is input 1, and this is input 2. So once we know input 1 and input 2, then we just say, okay, we just take the or of them, right? We just look at this and say input 1 or input 2. This tells us what to do depending on what those inputs are. So, okay, we just need to find these individual pieces. So P and Q. In this case, it doesn't really matter what R is, right? We don't care, right? Because it's not part of our input in this specific situation. We only care P and Q. What happens? So we just go along. Input 1 and input 2. P and T is P. F and T is F. T and F is F. F and F is F. T and T is T, F, F, F. Now we kind of look here, and since R isn't involved in that at all, if we look and cover that up, we've essentially got the same truth table twice, right? TT, FT, TF, FF, TT, FT, TF, FF. So when we look, we've got the same thing twice. Right, we can essentially cover this bottom half, and we've got the full truth table. But now we need to worry about not R. So that one's easy. It's just take this and flip it, whatever you see. So wherever you see a T, write an F. And wherever you see an F, we write a T. Like that. And now we see what we're interested in is taking input 1 or input 2. So now none of this stuff matters anymore. right? We just are going to take this or this. Well, the only time or is not true is when they're both false, right? So we just kind of look at that. P or F, that's going to be a T. F or F, that's an F. F or F. F or F. T, T. F, T. F, T. And F. And then just one last check. We go, okay, did I miss anything? 1, 2, 3, 4, 5, 6, 7, 8. No, probably not. So one thing that, so I don't have a ruler or a straight edge or anything like that. I don't care if you use one, but for building these, people like doing them because, you know, if you're just off by a little bit, then suddenly things start drifting together, right? Like you're drawing this, and let's just say it looked like this, right? No, I'll make it worse on purpose. So okay, this T goes with this one. It kind of looks like it goes with that, and then it starts bleeding together, right? Especially when you got a long chain of it, so it just becomes hard to like keep track of it. So you don't have to use a straight edge or anything like that, but it might be helpful to just like do this. You know, that sort of thing, just to keep it nice and, you know, a straight line, but not necessary if you don't want to. Yep.
The input one.
Mhm.
What is the difference between that equation and this one?
You mean this one and this?
Yes, it should be the same, right?
Well, no, because this is P and Q or not R. It's the whole thing taken together. Yeah. So we're essentially saying this is input one and this is input two, and now this is input one or input two, like combined together. Yeah. And so that's helpful because then we can build like way more complex things. So like imagine if not R involved a bunch of other stuff too, then we could sort of like build up to input one and build up to input two on the separate side and then just combine them at the very end. Okay, so let's just do another quick example. By the way, I'm probably going to be like everyone's worst enemy because it's like, what time is it? It's 6:30, and I'm going to like try to be super energetic and like excited, and everyone's going to be like, Travis, please, no. I just want to go to bed. And I'll be like, sorry, I'm excited about math. I'm going to be loud and obnoxious. Or I'll try to be anyway to keep people awake. Okay, so suppose we've got this statement. So this P, X, Y, X, Y, Z is that statement. So that means if we plugged in choices for X, Y, and Z, we are going to get a true or false value depending on what we plug in. So let's find the truth table for not P of X, Y, Z. So even though there's variables in there now, we don't care when we're building truth tables. And Q or R. Okay, so that's step one. We can build a truth table no matter what we're plugging in, right? Because the variables that we plug in, the X, Y, or Z, all those do is tell us whether or not it's true or false depending on those. But P as a logical statement still is only true or false, right? So these variables don't really matter for a truth table, right? It's a statement that's either true or false. So we can build a truth table all we want, but then let's use it to find the truth value when X is 1, Y is 2, Z is 3, and R is false. Okay, well that's interesting because this x, y, and z being determined here gives us a truth value for this thing, right? Now we know the truth value for r, but what about q, right? It can be true or false. So like, aren't we going to get two answers from this? That seems like essentially I'm asking you to return a value that is returned twice. It's two different things simultaneously. That doesn't seem like that should work. But let's just build the truth table and see what happens, right? So first we've got our p, x, y, and z, and then we've got a q, and we've got an r. We're going to do the same thing. We're just going to do that pattern. T, F, T, F, T, F, T, F. And now I'm going to have to write down at the bottom of the board, which is going to be painful. Now we just double the amount of t's we wrote. So 2, T, T, F, F, T, T, F, F. And then we double again. So now we write 4 t's and 4 f's. See, this is what I mean. Now it's starting to look a little funky. Okay, that should be better. Okay, so now we've got our inputs down. So again, we don't care about the x, y, and z right now. We're just going to figure out the truth values. So we've got our negation here. Right, if we look here, this is input 1. And then, hey, we've got this other statement here. That's our input 2. We got to figure that out too. And then from there, we write down the whole statement, right? P or not P of x, y, and z. Hopefully I have enough space here. Okay, so we just go one at a time. So not P of x, y, and z, we just flip the values, right? True becomes false, false becomes true. So F, T, F, T, F, T, F, T, like that. And then input 2 is similar to the last example we did. So this is Q or R. So that's these two things, Q or R. So the only time we write down F is when they're both F. So T, 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 F, F. Okay, now it's input 1 and input 2. So we just take these two things, and so long as they're both true, we write down true. Otherwise, we write down false. F, T, F, T, F, T, F, F. Okay, so that's our truth table. Great. But now we have the second question here, right? It says use it to find the truth value when specified choices. Okay. Well, what does this mean? What does P of 1, 2, 3 mean? Well, we just have to remember what the statement was. It was the first number plus the second number less than or equal to 3. Is that true or false? Right. Because this is 1 plus 2, which is 3, is less than or equal to 3. That's a true statement. Okay, so P of 1, 2, 3 is T, R is F. Right, that was given to us. R is F, P is true. So now we just take a look at this table and say, okay, well, when is P true? Here, 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 here. When is R false? So here, 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 and here. Well, where the blue and red are, those are the only situations, or where we have double lines like this and like this. Those are the only two situations where they overlap. So we just sort of draw dotted lines. This is line 1, 2, 3, 4, 5. Trying to make sure it goes across like that. Okay, so we get false. All right, this one is line 7. It's the second last one. False. Oh, so it doesn't matter what Q is, right? We didn't specify what Q had to be in this question, but it doesn't matter, right? We can kind of see here where we cross through. Q is T here, Q is F there. So both are fine. It doesn't matter, right? It can be true or false. Either way, the whole statement is false, right? So in this case, for specified inputs, the statement is false. Okay, so, I mean, you might be thinking, hey, why truth tables in the first place? And that's totally fair. It is mostly a logic thing or a mathematical thing. Technically, if you have a conditional statement, you know, composed of compound things, like you've got if something and bracket something or something else, you could build a truth table to find out, you know, when will this return true, right? And that can maybe be helpful. It's 2024 though, and for your Python class, did you use PyCharm? Okay, I mean, up to your choice, right? I mean, you could use PyCharm, you could use VS Code, whatever. But most of these things have pretty powerful built-in debugging tools. So, you know, if you're working in assembly, maybe building a truth table is going to be helpful because assembly is pretty awful to debug. So if you've got a conditional there, you might want to just work it out and be like, when do I expect it to be true and when do I expect it to be false? But modern day debugging, you would just have breakpoints and like just flow through the code and maybe change the values, see what happens. So that's theoretically a place where we care about truth tables. The place where we actually care about truth tables is when we're talking about logic circuits and hardware design. If you're actually, you know, drawing diagrams with like circuit diagrams, you will be drawing in logic gates, like, you know, like that, right? Stuff like that. You need to know what that means and what happens depending on the inputs, right? So that's where truth tables really shine. It's less building a truth table, a more just really understanding what's going on behind the scenes lets you understand those logic gates. And on the assignment, the bigger one, I kind of have you play around with like an online logic gate simulator. It's kind of fun to mess around with, and it sort of shows you how these truth tables do actually relate to, you know, circuit diagrams and computing. The real reason why is it gets people thinking about ands and ors and negation, you know, more complex conditional statements before they start programming, and for circuit design. Okay, so one more math definition. So this is a tautology, which is fancy logic words for essentially equality. It's the logic equivalent of equals. So a tautology is a logical expression that always evaluates to true. So that means no matter what you plug in, it's going to spit out true, right? No matter what. So the reason why I say tautologies sort of fill in the gap of equals in math is with some examples. Not all of them take this form, but like this is just sort of the easiest way to think about it. So something like this. P biconditional, not P. Now, in terms of math, this looks kind of like something we've seen. What's negative 1? 1, right? Yeah. So this is what I mean. It behaves kind of like equals in terms of rules, right? So we can describe a lot of rules here. I'm claiming this is a tautology in terms of logic. So let's actually see that, right? Let's actually work out the truth table for this. So this one's relatively simple. We have one input, and then we have not P, which is inside the brackets, and then we have not P, which, as a side note here, a lot of students will do these sorts of things in their head. So like you might not need to write down not P here. For the demonstration of this being true, we're going to do it, but like if you're able to do negation in your head, you don't have to write it down to show work or anything like that. It's okay to just, write down it. You better be confident though. So this is the thing I always tell students in math, within reason. They're like, do I have to show those steps? And I'm like, how confident are you? Because if you're very confident, then no. If you've got other explanations for everything else and you skip those steps, then sure, go for it. If you're right, I'll give you full credit. If you're wrong though, I don't know where you went wrong, and I can't give you partial credit. So you gamble with your grades. I can only grade on what I see. So if you write almost nothing and you're wrong, you get almost nothing. Now, on that note, that doesn't mean you just write down the correct answer and move on. I need you to show some work. Show me that you understand something. But there's intermediary steps where I don't necessarily need you to write literally every single step down, right? I can assume that you did it in your head sometimes. But just be careful that you're actually able to do it in your head and you didn't make a mistake. Okay, so we've got this whole statement here, right? We've got input 1. And then on the right side here, we've got this big thing here. And that's input 2. Okay, well, P can be true or false, which means not P is false or true. Now we take this and we negate it. We get true or false again. We just basically cancel it out. And now this is saying, check input 1 with input 2. Are they the same? If they are the same, write down true. So TT, FF, they're the same, so we write down true. So this statement is true no matter what. No matter what P is, we get a true statement, right? So this is what I mean by this word. It always evaluates to true, which means no matter what I choose for P, it will be true. And you can get more complex ones, right? You can have P's and Q's, and then your final result, this is just all T's. Everything is a T. And that's how you know, oh, okay, cool. Now what this means is for logic, just like here, every time we see a negative times a negative, we can write down the positive, right? We replace the negative with the positive. Logic is the same. When we've got this sort of tautology with this symbol, it means whatever's on the right-hand side, we can replace with the left-hand side whenever we see it, right? So it offers us sort of like a simplification method, right? If something more complex is on one side of this symbol, and we've got something here, and we've said it's a tautology, that's important. We've said that if we write down the truth table, it's all T's, then we can replace each other. So if this is a tautology, we can replace the left-hand side with the right. Now, I want you to be careful here. I say when it's a tautology. That doesn't mean every time you see this symbol, you can swap them or replace one with the other, right? It just means, it basically means we have a set of rules where you can do this. So we'll come back to them next week because this week we only care about the truth tables. But next week we're going to start talking about, hey, we've got ands and ors and this other stuff, and we've got negation. And now I'm saying, hey, we've got the equivalent of equality. Sure looks like we can do some kind of algebra with this, right? And we can. So there are a whole bunch of what I'm going to call known tautologies. We'll visit them next week. So they're actually in this section right here. I have, look at that, big old list. We're not going to talk about all of them. Some of them are, well, one of them is this, but some of them are what I would say are quote unquote obvious, right? So like the following: P or Q is equivalent to, and that's what this symbol really means, Q or P, right? Well, where have we seen that before? Right? In addition, you can, it doesn't matter which order you do them in, right? So like we've got a lot of these rules that are things that we take for granted in algebra. And it turns out, like at a deep fundamental level, why is this true? Because this is true. Well, there's an intermediary step. Because this is true, a set theory related thing is also true, which means this is true. So like this logic stuff is the fundamental building block of mathematics, which then gets us to here. And there's a whole bunch of these. Some of them are weirder, but like I said, next week, when we go more in depth into how all of this ties together to give us an algebra rule, it's called Boolean algebra, which just sounds so exciting. It sounds like I'm being sarcastic. I'm not. I'm an eccentric weirdo. I love math. I love Boolean algebra. So this does give us a set of rules that we can actually manipulate expressions and do simplification and stuff like that. And that's pretty cool. Okay, any questions? Or are you ready for a fun 7 p.m. quiz? Again, it's take home and open book and whatever, and you can work together. It's not like a stressful thing.
Would you say that we can replace the left-hand side with the right? How it looks like?
So that's kind of why I'm finishing off with this, because we're going to lead into that next week. So when we're doing like simplifications, so like if you had a more complex statement, like let's say you had not P and Q or R, this is the same thing as just writing P instead, right? So you could say, okay, that's P and Q or R. So like, let's say you were trying to build truth tables or whatever, or build logic gates, you'd be like, I can simplify this to this, right? And hold on, now I've said the word simplify. I need to go on a rant about that word. So in high school, did you ever face a situation where you were told, simplify this answer, and you were like, I've done that, and you handed it in and you got it wrong? Yeah, right? Because that word is terrible. So I hate simplify. I'm just going to write it on the board. I hate that word because it's context sensitive, right? So let's think of an example. And if you don't remember factoring and stuff like that, that's okay. You don't have to worry too much about it. So which is simpler between the following? which one's simpler? Who thinks this is simpler? Who thinks this is simpler? So we actually, people were split. That's exactly the point, right? Because it depends on what you're doing, right? So if you are trying to graph this thing on graph paper, this is the simpler form because this tells you information about the parabola. If you are trying to solve the equation or find the roots, this is simpler because this is the factored form, and this tells you the roots are 1 and minus 1. So again, if you're like, I don't remember polynomials, that's okay. Don't worry about it. My point is, depending on what you're trying to do, this is simpler or this is simpler, which means when someone says, simplify this as much as possible, you're like, what do you mean? I thought it was as simple as it goes. But because of that, and just the nature of the world, I still have to use that word. I still have to say simplify. So when I say simplify, it's usually quote unquote obvious in the context in this course. I would never do something like this where I'm like, pick one, and then one of them's wrong and one of them's right. Simplify usually means either in lowest form. So when we talk about simplify the following fraction, that usually means there is a stopping point, right? It goes as low as it goes, and there's no further. So that's what I'll say in this course too, is if it's not obvious, then I will say simplify it until it looks like this. So now you have a goal, right? So the simplify, what it means is specified. It's not just keep going until you feel like it's simple enough and hope you get all the marks. It's get to this point. If you didn't, then, well, maybe you'll get 4.5 out of 5, but like you didn't get to the finish point. But if you did, that still doesn't mean you get 5 out of 5 because maybe you made an error along the way. And if you make 2 errors, they cancel out and now it looks all right. But I just wanted to say that because like I don't like using that word, but we have to in math, right? It's just the nature of it. But I will probably never penalize you for not simplifying enough. This class ain't about that. So you don't have to worry about it, with the exception of if I say simplify it so that it looks like this. If you do not make it look like that, then that's less of a you didn't simplify enough. It's you didn't follow instructions. So it's a little different. Okay, sorry. It matters for next week. It's just because I was talking about simplifying in a way already. I was like, I'll just do it now. My next class, the previous class, they're gonna get it next week. The rant. Okay, so like I said, the structure is I do some lecturing, usually like 2-ish hours in a week, sometimes more, sometimes less, depending on the topic. And then I put up a worksheet on the board, which is extra practice, which I post solutions to. They're not ready yet. I have to do them like throughout the week, but I usually will post them before this is due, just so that you have extra references. And then this is the one that's for grades. The worksheets are just for practice, right? If you just want to work on something and you're like, I just want extra because I didn't quite get the topic, so now I want something that has solutions available, and then I can just work through them and ask Travis questions and whatever. That's what they're there for. So I'll usually just, I don't print them off. They're posted on Blackboard. Pretty much everyone has their computer. So I probably won't even bother putting them up on the whiteboard unless someone asks me to. And then I hand this out. It's on big paper, which I didn't mean to do. So do you ever have those days where it's like, man, this is the worst Monday ever. And then everyone's like, Travis, it's Wednesday. It's not Monday. And you're like, wow, awesome. That's me today. It's been like that. It's just been a weird, terrible day. So I accidentally printed it on long paper instead of short paper. But I guess that's not so bad for math, right? Because then you get more space to write on, which is nice, I guess. But usually I'll do it on the smaller paper because just carrying, like, try and put this in your binder or backpack. It's long and annoying. So on that note for this, because you can submit it online on Blackboard, I'm not holding you hostage. So it's 7 p.m. If you're like, oh, great, I just want to go home, feel free to. You can submit it online, but you can also stick around and work on it and ask me questions. That's what I'm here for. It's just answer questions about the quiz or anything, really. Oh, no. Oh, yeah. Sorry. It's due on Saturday. So you got lots of time. So that gives you time for, like, if if you want to just go home and stew on it and then send me an email or be like, Travis, can we meet on Friday or something and talk about it? You can. There you go. There you go. Yep, sure. I got one second. Saturday. Yeah. The sheet? Yeah, so I didn't even do it on purpose. I just printed the printer and I walked away. I came back and I had 70 people. I was like, yeah, I don't know. There you go. You betcha. There you go. Here, I'm going away for You betcha. Yeah, there's only one question. Generally, it'll only be one question. The quizzes are just meant to be like, are you doing what I said in class? Really?